tutors for today,
and we'll be teaching you linear programming method. I am Cris.
I am Demi, and I am Shantyl.
What is a linear programming? Linear programming is a widely used mathematical modeling technique designed to help managers in planning and decision-making relative to resource allocation.
One of the ways of solving a linear programming problem is the graphical solution method. So to expound our knowledge of graphical solution method, let us solve this problem.
First step we're going to do is to construct first our decision variables. So we will let our x1 be the number of grams for brand A and B, and our x2 be number of grams of fats for brand A and B. Second step we're going to do is to create a table so that it will be easier for us to analyze and formulate the objective function and its constraints. So for protein, we have 15 for brand A and 20 for brand B. For the fat, we have 10 for brand A and 5 for brand B. For protein serving, we have 60 and 30 for the fats. So for the cost for brand A, we have 80 cents per unit or 0.8, and for brand B, 50 cents or 0.5 for the brand B. So we now have our objective functions, which is to minimize the cost of the rancher equal to 0.8 x1 plus 0.5 x2. And for the constraint 1, which is 15 x1 plus 20 x2 greater than or equal to 60. And for the constraint 2 is 10 x1 plus 5 x2 greater than or equal to 30. And the non-negativity greater than or equal to 0.
In getting the coordinates for both constraints, we need to solve for x1 and x2 intercept. So for constraint 1, we have 15x1 plus 20x2 greater than or less than 60. So we let x1 is equals to 0. So 15. Obtaining x2 is equals to 3. So we let x2 is equals to 0. 15x1 plus 20 times 0 is equals to 60. So cancel the 0. So x1 will be equals to 4. For constraint 2, we have 10x1 plus 5x2 greater than or equal to 30. So we let x1 is equals to 0. So 10x times 0 plus 5x2 equals to 30. So cancel x2 is equals to 6. We let x2 is equals to 0. So 10x1 plus 5 times 0 is equals to 30. So we get x1 is equals to 3. So we now obtain the coordinates for each constraint. For constraint 1, we have 4 and 3. And for constraint 2 is 3 and 6. Based from the solution, we graph to get the corner points and the shaded area is called.
To solve for the optimal solution points, we will use the elimination method for the two constraints. We simply multiply to the second constraint with negative 4. And then the next step will be adding the two equations. Now we obtain x1 having 2.4. The next step will be to substitute x1 to constraint 1. Then we now have 15 times 2.4 plus 20x2 is equals to 60, and 36 plus 20x2 is equals to 60. We now transpose 36 to the other side, so we have 20x2 equals to 60 minus 36, and then we have 20x2 equals to 24, and then we eliminate 20, and then now we obtain x2 equal to 1.2. Now we obtain the values for x1. We have 2.4, x2 equal to 1.2, and then we now substitute it to the objective function. We have 0.8 x1. We need to multiply it by 2.4 plus 0.50 x2, multiply it by 1.2. And then we now get the objective function $2.52.
Hola amigos! This time, we're going to solve a maximization problem of a linear programming topic. First step we're going to do is to construct first our decision variables. So, we'll let our x1 be our alpha 4 and our x2 be our beta 5. Second step we're going to do is to create a table for us to easily analyze the problem and formulate the objective function and its constraints. For the required labor hours, we have 20 for the alpha 4 and 25 for the beta 5 with an available time of 800 hours. For the required minimum number of units, we have 10 for the alpha 4 and 15 for the beta 5. And for profit per unit, we have $1,200 for the alpha 4 and $1,800 for the beta 5. The profit of each model for the mini computer, which is equals to 1200 x1 plus 1800 x2. And for the constraint one, which is the required labor hours, we have 20 x1 plus 25 x2 less than or equal to 800. And for the constraint 2, we have x1 greater than or equal to 10, which is the required minimum number of units for alpha 4, and x2 greater than or equal to 15, which is the required minimum number of units for beta 5, and our non-negativity constraint, which is xi greater than or equal to 0.
In order to get the coordinates of constraint 1, 2, and 3, we will solve first the x1 and x2 intercept. So for constraint 1, we have 20x1 plus 25x2 less than or equal to 800. Let x1 is equals to 0. So 20 plus 25x2 is equals to 800. We obtain x2 is equals to 32. Let x2 is equals to 0, so we have 20x1 plus 25, substitute it with 0 is equals to 800, cancel, so we get x1 equals to 800 divided by 20, x1 is equals to 40. For constraint 2, we have x1 greater than or equal to 10, so we directly solve for x1, which is it is equal to 10. To solve for constraint 3, we have x2 is greater than or equal to 15. So we directly solve x2, which is equal to 15. The coordinates for constraint 1 is 40 and 32. For constraint 2 is 10 and 0. And for constraint 3 is 0 and 15. Based from the coordinates solved in getting x1, x2, and x3 intercepts, we then graph the coordinates to get the corner points. The shaded area is called the feasible region.
To solve for the optimal solution, we will use the corner point method, which are points A, B, and C. For point A, it consists of constraints 2 and 3. We have x1 is equal to 10 and x2 is equal to 15. So we simply substitute it to the objective function. So we now get $39,000. For point B, it consists of constraint 1 and constraint 2. For constraint 1, we have 20x1 plus 25x2 equals to 800. And for constraint 2, we have x1 is equals to 10. So we simply substitute x1 to constraint 1. So here we have 20 times 10 plus 25x2 is equal to 800. And we have 200 plus 25x2 is equals to 800. And now we transpose 200 to the other side, so it will become negative. So 25x2 is equals to 800 minus 200. And then we divide 600 to 25. So now we have x2 equal to 24. And then we simply substitute x1 is equals to 10 and x2 equals to 24 to the objective function. We have 1,200 times 10 plus 1,800 times 24, we obtain 55,200.